Welcome to lab number 4 using bar magnets. The purpose of this lab was to measure the distance dependence of the magnetic field of a bar magnet. We compared our measurement of distance dependence due to the off-axis bar magnet and the on-axis bar magnet. As a result, we found that n is equal to negative 1.6 and the magnetic dipole moment of our using our data was 0.26. Here are the fundamental principles of this lab. First, we use Biot-Savart law. This equation describes the relationship between a magnetic field and a constant electric field. The next two equations show how we will determine the magnitude of the magnetic field caused by the magnetic dipole. These equations will be important when we are solving for the magnetic dipole moment. This equation to the right linearizes the data that we collected in our lab. Finally, we will use this equation in the computational model to calculate the magnetic field at any point due to a magnetic dipole. Here was our experimental procedure. First, we calibrated the magnetometer in the phone by aligning it with the Earth's magnetic field. We do this by rotating the phone till we reach a 0x component in the B field. Then we find the location of the magnetometer in the phone using the tape. Finally, we will measure the distance between the magnet and the magnetometer for both off and on-axis measurements. Here is the experimental setup as shown in the diagram below. Here are the data for our on-axis measurements. We found the distance required for the B field to be 20 microteslas, 70 microteslas, 120 microteslas, 170 microteslas, and 220 microteslas. From this, we graphed the data and we linearized the data, and we got a line of best fit of y is equal to negative 1.66x minus 16.759. Then we set both of these equations equal to each other and solved for mu, which is the magnetic dipole moment. We said that n is equal to the slope, which is negative 1.66. Then we isolated k, which turned out to be 5.27 times 10 to the negative 8. After setting them equal to each other and isolating mu, we got that the magnetic dipole moment was 0.2635 ampere per meter squared. Here are the off-axis measurements. They were taken the same way as the on-axis measurements. However, the setup was a little different, as it was now a distance d from the bar magnet instead of being parallel to the magnet like in the previous setup. From this, we were able to get that the net average B field from the perpendicular measurements was 0.000285 teslas. Here's the code for the computational model. First, we defined a function that would calculate the magnetic field of a dipole. Then I created an observation location for the perpendicular and on-axis observation locations. Then we created the arrows that would represent the on-axis and perpendicular measurements. Finally, we created the visualization of the magnet and specified the calculated magnetic dipole moment, which we calculated in the observed model. Here is our computational model. As you can see, the blue arrows represent the perpendicular measurements, the orange arrows represent the on-axis measurements, and the magenta arrow represents the B field at a 45-degree angle. As you can see here, the distance 0.1697 is the same calculated distance from our observed model. However, the B field at a 45-degree at a distance d is off by a factor of 100. This could be explained by some of the human error that we introduced in our lab, which we'll discuss in the next slide. Here are our possible sources of error. The first possible source of error was that there were other objects in the nearby vicinity of the magnetometer that could create a magnetic field. These objects included wires that ran through the table or our devices like our laptops and phones. The other error was that there was no guarantee that we found the exact position of the magnetometer in our phone when we first calibrated the magnetometer. Finally, one of the assumptions that we made in this lab was that the magnetic field drops off due to distance. However, this could be a wrong assumption because other objects other than the magnitude that produce a B field could be present in the opposite direction of the bar magnet. The first statement is true because the magnetic field decreases as you get farther away from the magnet. The second statement is false because the magnetic field should increase as we get closer to the magnet. This third statement is false because the magnetic field varies with position. Therefore, moving the magnetometer changes the x component of the magnetic field it measures. The last statement is true because the magnetic field increases as you get closer to the magnet. If we had not compensated for the magnetic north and instead laid out our meter stick at some intermediate angle with respect to the Earth's magnetic field, then the Earth's magnetic field would interfere with the bar's magnetic field and would affect our overall results. The second what-if question: If we were to stick two identical magnets together end to end, our measurements would double in magnitude and stay in the same direction. In conclusion, this lab helped us observe how the B field is dependent on the distance for both on-axis and perpendicular measurements. Thank you for your time.